Another part of thermodynamics is looking at whether a process is spontaneous, meaning whether it will occur without any outside intervention. It happens naturally by itself. We're not talking about how fast it's going, but just whether the reaction would occur by itself without any outside intervention. For example, when you put sugar in water, it spontaneously dissolves without any outside intervention. Eventually that sugar will dissolve in water. If you spray perfume in a room, you'll notice that without any outside intervention, eventually you'll smell it on the other side of the room. The gases naturally expand into a container. Rusting, again, is something that occurs naturally without outside intervention, which we say is spontaneous. Again, this gives no information on the speed of a reaction. Like diamond will naturally turn into graphite, and it happens very slowly over time, but it does happen. So this is nothing about speed. We'll look at that in a different chapter called kinetics, but just whether or not a process is spontaneous, meaning will it occur without any outside influence. So, which would occur spontaneously, again, without outside intervention? A reaction that's exothermic, which releases heat, or a reaction that's endothermic, requires heat? Let's think about it. If you think of your potential energy diagrams, okay, here's an endothermic graph. Overall, we're going up from reactants to products, so energy is absorbed. Here's exothermic. Overall, we're going down. Same reaction, but different sign of delta H. So I'm just flipping it one way or the other. So notice that if I am going to find the activation energy, the energy needed to start the reaction, it's always going to be higher in the endothermic route. So it's always going to require a little more energy to start an endothermic reaction. So therefore, exothermic reactions, because they have a lower activation energy, are typically more favored. They're more likely to happen naturally without outside intervention. So we can say that enthalpy, or delta H, is a factor that drives a reaction. Exothermic reactions, ones that have a negative delta H, are more spontaneous, or we say are more favorable, and reactions tend to be driven toward lower energy. So we'll see this trend in nature towards going toward lower energy. That's why a lot of times bonds are made. You can find elements in compounds because it is more stable, lower energy to be in a bond, and forming a bond exothermic. So the same thing, that this nature is driven toward lower energy. So here's a question. Here is a dissolution reaction showing NaCl solid breaking up into its constituent ions when dissolved in water. And notice that the delta H is positive. This is an endothermic process. Would the following reaction occur spontaneously once salt is placed in water? Well, just based on observation, what happens when you put salt in water? Does salt dissolve? Yes, it does dissolve when I put it in water. Without any outside intervention, if I drop salt in water, it will eventually dissolve. So even though it's endothermic, we know that salt will spontaneously dissolve when placed in water. So there must be another factor that drives reactions aside from enthalpy, aside from delta H. What do you think this factor is? This factor is entropy. So there's going to be two things that we look at to figure out if a reaction is spontaneous or will be favorable or will proceed forward. And that's enthalpy. We want to go toward lower enthalpy for the most part, and entropy. Entropy is kind of a measure of disorganization or disorder. Nature tends toward a more random arrangement of molecules. This is also because a disordered arrangement is much more probable than ordered arrangements, which we'll take a look at. Entropy, we're going to give the symbol S. Change in entropy will give delta S. So entropy is a measure of the disorder of the system. It's really helpful to think of this other definition of entropy as being a measure of the dispersal of matter and energy. Anytime matter or energy is becoming more dispersed, you are increasing the entropy of the system. And it's going to be helpful to think of it in that way when you are figuring out if entropy increases. So the more a substance can disperse its matter or energy, the more entropy it has. Or you can also think of it, the higher the degree of randomness, the higher the entropy. Overall, if the entropy or disorder of a reaction increases, delta H is going to be positive. If it's positive, another way of saying that is delta H is going to be greater than 0. You'll see that a lot in AP questions. Rather than saying positive or negative, sometimes you'll see greater than or less than 0. And some people don't really like seeing that, but you might want to get used to it. The overall entropy or disorder of a system will decrease if delta S is negative or less than 0. So a reaction is going to be spontaneous. Usually if delta S is positive or increasing or greater than 0, as nature tends to go toward increasing entropy. So again, nature is going to tend to go toward lower enthalpy, lower delta H or negative delta H, but toward higher entropy or increasing entropy or positive delta S. And as a note, unlike energy, there's conservation of mass law, there's a conservation of energy law, but there is no conservation of entropy law. Entropy is actually not conserved. The universe is going toward increasing entropy, and that's one of the laws as well, saying that entropy is not conserved. The universe is going toward increasing entropy. So even if we think about, okay, here's a gas, here's a valve that's shut. Once I open that valve, we know that this gas just naturally, again, spontaneously, without outside intervention, is going to eventually disperse throughout throughout both bulbs in this vessel. So why does this gas expand to fill the container? Because entropy is increasing. What do we say entropy of? Is dispersal of matter or energy. The gas is becoming more dispersed, entropy is increasing, so this is spontaneous. We said systems tend to go toward increasing entropy. Why do substances go toward increasing entropy? You can also think of it in terms of probability. Substances are going to take the arrangement that's most likely to exist, and the most likely is the most random. So if I just show this, okay, here, why do gases disperse through a container? Let's think of 4 molecules, okay, in this same kind of bulb situation once I've opened the valve. So if I have 4 molecules, I could either find them all on the right, all on the left, 3 on side 3 and 1, 3 and 1, again moving the possible arrangements around, or 2 and 2, and again you'll see all the possible arrangements. I can see these 4 different molecules. So there's 12 possible arrangements. Look at this, there's a 50% chance of them both being found evenly dispersed, where it's dispersed throughout both sides, 2 and 2. There's only an 8% chance of finding the left side empty or the right side empty. So it's more probable for nature, more probable in nature for the system to be more dispersed in matter or energy. Okay. A lot of the times when you're thinking of entropy, if you're looking at a reaction and you want to know, does entropy increase, you're going to be looking at phase. So which phase, solid, liquid, or gas, has the greatest dispersal of matter or energy, or is most random? A gas. So a solid has less entropy than a liquid has less entropy than a gas. Gases are the most random or the most dispersed, so they would have the most entropy. So anytime you see a reaction that's going from like solid to gas, you are increasing the entropy. Delta S is going to be positive. Okay, you can also look at entropy in terms of a mixture versus the separated compounds. Again, there's going to be this natural tendency for substances to mix because this is going to increase the randomness or the dispersal of matter. So a mixture is always going to have more entropy than separated compounds that are not in a mixture. So if I'm going kind of back to phases here, a solid would be less than a liquid. Aqueous would be more randomized than that because, again, that is a mixture, not a pure liquid or pure solid, and a gas would probably be more entropy than that. So when will entropy increase? Entropy is going to increase in a system if liquids or solutions are formed from solid. If you see something going from solid to liquid, or liquid solid to an aqueous solution, something's dissolving, entropy is increasing. Also, anytime you form a gas from a solid or liquid, entropy is going to increase. Entropy will increase anytime you see the number of gas molecules increasing. So if you see 2 moles of gas on the left but 4 moles of gas on the right of a reaction, entropy has increased. If the volume of the gas increases, again, you have matter that's more dispersed. So again, entropy would increase. So really going by that definition of entropy being the dispersal of matter or energy. Anytime you really have an increase in the number of product species due to stoichiometry, you're going to have an increase in entropy because, again, matter is more dispersed. Also, anytime the temperature increases, as the temperature goes up, particles are moving faster, and both matter and energy would be more dispersed or more randomized. So take a moment, try this example, predict the sign of delta S for each of these changes that are occurring. Then check your answer. So the evaporation of alcohol, it's important to know what evaporation means. So you're going from the liquid to the gas phase. So entropy would be increasing. You have more disorder or more dispersal of matter and energy in the gas phase than you do in the liquid phase. And I don't know why I wrote solid there. It should be going liquid to gas. The freezing of water. Okay, what does freezing mean? Freezing is going from a liquid to a solid. So you're going to have less disorder or less dispersal of matter and energy. So delta S would be negative or less than 0, which mean the same thing. Compressing an ideal gas at constant temperature. So if I'm compressing, the volume's going down. So I would actually have less dispersal of matter and energy. So delta S would be negative. Heating an ideal gas at constant pressure. So the temperature would be going up, so I would have more dispersal of matter and energy. I can also think of it as if the pressure is being constant and the temperature is going up, the volume would also most likely go up because volume and temperature are directly proportional at constant pressure. So if there's more volume, again, more dispersed. So either way I think of that in terms of temperature or in terms of volume, I should get that delta S is positive. And dissolving NaCl in water. Okay, if I'm dissolving NaCl in water, it's going from solid to aqueous. I'm forming a mixture. These ions are coming apart and being more dispersed in my water, so my delta S is positive. Anytime I'm going into solid to aqueous, it is increasing the delta S. Now, a quick question, a review of delta H. For A and B, what would be the sign of delta H, the enthalpy of these reactions? Well, evaporation's going from liquid to gas, okay? Freezing's going from liquid to solid. We're talking about phase changes here, so it's really helpful to kind of visualize my heating curve. So remember, anything going up the heating curve, heat must be absorbed to happen. Delta H would be positive. Anything going down my heating curve, like liquid to solid, delta H would be negative. So let's get a visual of that because they love on the AP to ask about phase changes. What's the sign of delta S versus what's the sign of delta H? So remember, delta S is all about randomness or dispersal of matter, and looking at phases can be really helpful to figure that out. Delta H is about heat absorbed or released, and if we're talking about phase changes, visualizing or just jotting down, drawing on the side of your paper if it's a test, a heating curve can be really helpful. So if I think of my heating curve, for instance, here's H2O. Okay, this is a solid until it reaches the melting point where I have both solid and liquid present. The melting point's at 0 degrees for water in Celsius. Then if I keep heating it, okay, now it becomes a liquid and the temperature changes again until the temperature becomes constant, at which point it boils, at this case at 100 degrees Celsius. And this is where I have both liquid and gas present, and then I have a gas. So I can think of any phase changes. So even though the phase changes are on a flat line and temperature's not changing, if I just kind of use as a visualizing tool, anytime I'm kind of going up this heating curve, it would be an endothermic change. And anytime I'm going down would be an exothermic change. So if I'm going up, okay, solid to liquid to gas, heat would be absorbed. So delta H would be positive. What about delta S if I'm going from solid to liquid to gas? Delta S would also be increasing. So anytime where I'm going up this phase, this heating diagram, delta H is increasing and delta S is increasing. Again, even if I'm on a phase change, it's actually the flat part of the line, but again, we're just using this as a visualization tool. And now anytime I'm going down, like gas to liquid or liquid to solid or gas to solid, delta H would be decreasing. It would be exothermic reactions because heat would be released. And this just makes sense. If you're thinking of if you have to boil water, you need to put a pot on the stove and add heat to it for it to happen. It's a positive endothermic reaction. So again, and delta S would be negative, gas to liquid to solid, less dispersal of matter, less randomized. And hey, notice that for these phase changes, the signs are the same. They're either both positive or both negative. Now that's not going to be true for different chemical reactions, but for phase changes, of keeping that same substance, just changing from solid to liquid or liquid to gas, these physical changes, these signs match, which is interesting to know. So for example, H2O gas to H2O liquid, predict what delta H would be, predict what delta S would be in terms of sign. Okay, gas to liquid, okay, it's like I'm going down this heating curve. Okay, delta H would be negative, it's exothermic, heat would be released, or delta H would be less than 0. And delta S would also be negative, going gas to liquid. It's less randomized, it's less matter being, or energy being dispersed. Okay, what about if I say CO2 sublimes? And this is a reminder to make sure you know the names of those phase changes. Sublimes is just the verb of sublimation. Sublimation, as a remembrance tool, starts with an S. It goes solid to gas. So delta H would be positive. Delta S would also be positive, going solid to gas. Make sure you know the name of gas to solid, which is deposition. Make sure you know the name of gas to liquid, which is condensation. Take a moment, try this example, predict whether the entropy increases, remains constant, or decreases for each, and then check your work. Ice melting is going from solid to liquid, so you are increasing delta S. A precipitate forms in aqueous solution, so that means you're going from aqueous to solid, so you would be decreasing the delta S. You're forming a pure solid from a mixture. A solid dissolves in water, a solid turning into aqueous, delta S would be positive. You're increasing the disorder, or you are increasing the dispersal of matter and energy. A gas condenses to a liquid, gas to liquid would be a negative delta S. And here's just the explanations if you'd like to see them. Take a moment and try this example, and then check your work. Okay, notice here I'm going gas to gas, but look at the coefficient in front. Here I have 2 moles of NO2 gas changing into 1 mole of N2O4. So I'm going from more gases 2 to less gases 1. So entropy would be decreasing. Anytime you're going to less numbers of gases, so coefficients matter. And it kind of makes sense. I have 2 moles of gas, or 2, if I even want to look at the molecule level, 2 molecules turning into 1 molecule, I'm going to have less dispersal of matter. H2O liquid to gas, okay, that's going to be positive. I'm creating more gases, more randomized. Solid and 1 gas turning into 2 gases, delta S would be positive. So notice, looking at the phases here to determine entropies, or the change in phases, is very important. Don't forget, entropy also depends on temperature. If you look at this Maxwell-Boltzmann distribution curve back from the ideal gas chapter, it shows as you increase the temperature, remember that this graph kind of moves to the right and it spreads out. So it's showing that the particles on average are having higher velocities and higher kinetic energies. So basically you have a greater dispersal of matter and energy as you increase the temperature, and therefore you have an increase in entropy. So when the temperature goes up, entropy goes up. Now, how do you calculate entropy? Entropy can be determined from complicated measurements, which they've done in the lab, and they tabulate standard molar entropies. This is kind of similar to the concept of heats of formation for different substances. You'll have that standard sign with that degree sign, meaning at standard state conditions, 25 degrees Celsius, 1 atmosphere, or 1 molar concentrations. But these have units of joules per mole Kelvin. Remember, delta H had units of kilojoules per mole. Why is temperature Kelvin in the denominator? Because remember, entropy also depends on temperature. So if these substances are at different temperatures, they are going to have different energies and entropies associated, with them. Also, standard molar entropies of elements are not 0. Remember when we were doing heats of formation, if you saw like an element in its standard state, how you would normally find it, like O2 gas, we said, oh, the enthalpy of formation was 0 because it took no energy to make that. That's not true of entropy. O2 gas would have entropy associated with it. It would have a lot of entropy because it's a gas. So everything is going to have an entropy value. There are no zeros. And it's also an extensive property, just like heats of formation. So you have to look at the coefficient in the reaction and multiply tabulated standard molar entropy by the coefficient. So just like how we did delta H from the heats of formation doing products minus reactants, you can do the same thing for entropy. You can find the delta S for that given reaction by doing the sum of the products times their coefficient minus the sum of the reactants times their coefficient. Again, you will not have any zeros in there like heats of formation. Everything's going to have some type of entropy associated with it unless it's at absolute zero, and that's when the entropy would be zero. This is on your formula sheet, but they don't mention the coefficients, so don't forget to multiply by coefficients. So take a moment, or just take a look at this reaction. So if I had this reaction, what I would be doing to get the delta S, I'd be doing 2 times the entropy of NH3 minus the sum of the reactants, 1 times N2s, and 3 times H2s. Now in your textbook you might have to look up these molar entropies. If it's an AP problem or a test problem, they'd be given in the problem statement. Okay. Since you're multiplying by coefficients, essentially your end result for delta S for the reaction is going to have units of joules per Kelvin because it's going to be the heat associated, and if you wanted to actually get this into joules, you have to multiply by the temperature to cancel out the kelvins, because remember that this is going to depend on what temperature you're at, because entropy depends on temperature. Higher temperature, the higher the entropy. Take a moment and just try this example. You'll end up getting delta S in units of joules per Kelvin, and try this example, then check your work. So I'm just doing sum of the products minus sum of the reactants each times their coefficient. Notice there are no zeros. Even H2 gas does not have an entropy of 0 to start with. It's a gas and it's higher than the others because you have solid, liquid, and aqueous. And I'm just doing products times reactants times their coefficient, and I should get negative 11.